So welcome everyone to the March BGC webinar. Our speaker today is Chris Jones from the Met Office, Hadley Center, and he's going to talk about carbon cycle results in CMIP6. Go ahead, Chris.
Great. Okay. Well, first, thanks guys for inviting me. I was going to say it's exciting to join a meeting remotely, but after the last 2 weeks, it's kind of a bit more business as usual than we might have expected. So yeah, I'm going to talk about carbon cycle results in CMIP6. It's been a major focus for the UK for the last couple of years, building our latest system model and running the CMIP6 experiments. So I know it's the same for you. So hopefully now all of that is starting to come to fruition. We had kind of a handful of papers being submitted before Christmas for the IPCC deadline. So this is kind of like the payback time for those years of hard work of building the model. So I'm going to talk a little bit about the background of the carbon cycle. I'm kind of assuming that most people listening to this are kind of in the Earth system modeling realm, and you've got a general sort of knowledge of why we do carbon cycle background, but I thought I'd give a little bit of history and talk about some of the concepts of the feedback terms and where the uncertainties lie in the system, and then discuss some of the results from CMIP6, so two particular MIP activities, C4MIP and a new one called ZEC-MIP, which I'll explain, and then a few concluding thoughts in terms of where I think CMIP6 has been successful or not, and sort of some areas for future. So this is sort of like the motivating graphic, if you like, for a lot of carbon cycle research. So it was one of the key messages from AR5, the last IPCC report, that the long-term warming is almost linearly related to the total amount of CO2 emission and much less dependent on the pathway of the emissions. So for a given warming target, we have a total carbon budget, and we can either emit more now and less later, or we can spread it out more in time. So it allows us to sort of decouple some of the physical aspects of the problem from the socioeconomic ones. And kind of coming up with this line sort of folds all of climate science into a single straight line, which is quite remarkable. So it's got all the carbon cycle feedbacks, the land and the ocean. It's got the whole physical system with cloud feedbacks and ice and ocean circulation, and it all collapses nicely onto a single straight line. And this is called, sort of known as the transient climate response to cumulative carbon emissions. So that phrase TCRE will come up a few times. So I'm going to talk a little bit about how do we actually arrive at this relationship. And what you can see is there's a fair amount of spread across that sort of orange plume. So if you wanted to read across from a temperature target of 2 degrees to come up with a carbon budget, there's a fair amount of uncertainty. So it's important to understand the natural carbon cycle and its feedbacks and see if we can try to reduce some of that uncertainty. So that leads us into really what C4MIP is about. So C4MIP is the coupled climate carbon cycle model intercomparison project, and it dates back quite a long time. So if we look back right into the 90s, I joined the Hadley Center in 97 and worked with Peter Cox and others, with Richard Betts, on building kind of like the first couple carbon cycle GCM. And that paper came out in the year 2000. And shortly after, the French group, Jean-Louis Dufresne and Pierre Friedenstein and people, also published a similar study with their model. And the Hadley Center model had a really strong feedback between climate and the carbon cycle, and the French model a much weaker one. And Pierre derived shortly after that a sort of feedback framework to quantify the different parts of the system into what we kind of now know quite well as the alpha, beta and gamma terms that I'll describe a bit more later. And then because these two models were very different, this led to the initiation of an intercomparison across different carbon cycle models. So that's kind of the start of C4MIP. And stage one of that was to run lots of carbon cycle models and, as it turned out, get lots of very different results, which is quite often what happens when you run lots of models, right? So that led to Pierre's paper in 2006, and I'll refer to that throughout this talk as C4MIP. So it's a little bit confusing. C4MIP is both an ongoing activity, but I'll also use it to refer to this first generation, and subsequent generations were part of the wider CMIP activity, so the CMIP5 and now CMIP6. So hopefully that makes sense. But in terms of understanding what was going on in those models, it was rapidly clear that most of the spread between the models was in the land surface and not the ocean carbon response. And there was initially some focus on soil carbon as the biggest store and its sensitivity to temperature, so things like the Q10 response. And Damon Matthews did some nice work early on as well, looking at the sensitivity of vegetation productivity, so MPP, as a control on the climate feedback. But most of these early studies sort of fixed on the fact that it was the response to climate that was the big uncertainty. So we were looking at simulations with and without climate change and how they affected the carbon cycle. Later on, Jonathan Gregory had a paper that, even though we already had these kind of beta and gamma terms to split up the response to CO2 and climate, it was Jonathan's paper that really stressed that we needed to see those things as two kind of really separate and competing processes. And I'll talk a bit more about the implications of that in a minute. Okay, so then we came to CMIP5, and unfortunately a large uncertainty remained. So again, we ran lots of models, and there was a big spread of models, spread of the feedback, so there was a spread of their projections. So there's a handful of papers looking at the feedback terms and the compatible emissions, and the IPCC had a large section in the carbon cycle chapter looking at these feedbacks. And it was perhaps disappointing that the spread was no better than in C4MIP, although kind of this is sort of inevitable when you do big multi-model studies. But I think what we found was that even though the model spread wasn't reduced, we've learned by that stage to use the results better. So we were understanding that there was a state dependence and a rate dependence of the feedback factors. So you can't transfer the feedback terms from a fast to a slow or vice versa scenario. You can't take a paleoclimate proxy, for example, and apply those numbers to a future projection. And more importantly, there was this idea of a link between the cumulative emissions and the total amount of warming. And there were a handful of papers that came out in 2009 that explored this. So this is this TCRE approach. So even though the spread of models was no better than the first generation of C4MIP, we could actually do something more useful with them and start to constrain a carbon budget. But of course, no sooner have you made a simplifying assumption, then people start trying to make it complicated again. And there's lots of literature since AR5 kind of exploring all the different assumptions that go into what you then have to do to get a carbon budget. And that led us to the special report on 1.5 degrees that came out in 2018. And what they did in there was a kind of quite a careful and robust sort of unpicking of all the different terms and the assumptions that go into carbon budgets. So there's more than just this TCRE number. And they came up with this framework. So I've got some slides here courtesy of Yuri Rogley and his paper from 2019. But this is the sort of the decomposition they used in the special report to split carbon budgets into 5 distinct components. So imagine you've got a global warming target, say 2 degrees or 1.5. First thing you need to do is understand where we are at the moment. So you need some estimate of the warming to date. And it's important to note here, this is the human-induced warming, so not necessarily the observed warming, although they tend to be very similar. And we don't need to go into details around the exact choice of pre-industrial baseline or metrics for surface air temperature or mean surface temperature, but there are various assumptions that go into your definition of warming to date. But then you can stick your straight line through there and have some uncertainty spreading out from that. So this is your TCRE relationship that relates subsequent warming to cumulative emissions from today. And you could just read off a carbon budget from the top there, but there are a couple of other things you need to account for first. So the first one is what we call the zero emission commitment, the ZEC, and that we'll talk about a bit later. So we have an entire MIP dedicated to looking at that. So in the special report in 1.5, they assumed, as per AR5, that this was zero or very close to zero. For reasons it turns out are quite reasonable. You then have to account for the non-CO2 contribution. So obviously if you care about other gases, particularly methane, but other greenhouse gases as well, you have to aim slightly lower than your global target for CO2 to allow for that. But now you've got this kind of what you might see as remaining allowable warming, you can read off from the TCRE line to get a remaining carbon budget. And then the final step, so this is 4 components, the final component is to reduce your carbon budget or possibly increase it, depending on the sign of this term, by any feedbacks or processes that are not resolved in your Earth system models. So your definition of TCRE tends to come from the Earth system models. And if you've got a feedback process, so permafrost is the example people normally use, that's not represented in that TCRE line, you need to then adjust your remaining carbon budget. So this was kind of like a really nice kind of step through all the different terms in the carbon budget. And that brings us back to kind of carbon cycle simulations now, because the carbon cycle is sort of responsible for 3 of these 5 terms. So the TCRE gradient, the zero emission commitment, and then the additional feedbacks. And TCRE and the ZEC I will talk about in some detail during this talk. So that brings us to the question then, what's required now from CMIP6? And the first nice thing is, well, now we can insert some new model results into the 1.5 framework. So at the time, even though that was a kind of a really nice exploration of the different terms in the process, the 1.5 degree report didn't have any new modelling results, so it still drew on the CMIP5 models. So hopefully with CMIP6 we'll be able to do stuff possibly to reduce uncertainty, improve our knowledge on carbon budgets, and therefore improve policy advice how to meet climate targets and avoid impacts. At least that's the end goal. Right. One more thing I wanted to go through before we get into results is just a quick discussion on feedbacks and how we came up with the carbon cycle feedback framework, and possibly some of the pitfalls in terms of over-interpreting similarities with the physical system. So if you imagine schematically what the climate system feedbacks look like, if you imagine Earth's energy budget, and if you were to somehow alter the top of the atmosphere balance, for example with letting more energy in or preventing energy leave, which is what greenhouse gases do, then of course what you get is a change in global temperature. So the Earth warms up, and in response you get more energy out. So this is kind of the black body response or the Planck response, and that's pretty well known, and being proportional to T to the 4, it's an extremely strong negative stabilizing feedback. So we've got this kind of fundamental response of the system that opposes any perturbation, but on top of that we get other feedbacks. So we know that clouds change, water vapor, ice albedo, the ocean heat uptake, and from modelling the sum total of those is a positive effect. So it's an amplifying feedback, although we know that some of those terms can be of either sign, both locally or globally. So cloud feedbacks, for example, can change depending on whether they're low cloud or high cloud, or daytime or nighttime. But overall, we know that those are positive feedbacks, and they amplify the response you get relative to if you only had the black body response of the planet. So now we can kind of draw some parallels to the carbon cycle. So I've deliberately kind of kept the figure the same. So if you imagine now anthropogenic emissions are putting more carbon into the atmosphere, and then carbon is being removed to land and ocean sinks. So obviously it's not going out into space like this figure implies, but that's just kind of for a parallel with the energy. But these kind of natural sinks are driven primarily by the increase in CO2, and that's the equivalent to the Planck response, and it's this strong negative stabilizing term that if you put more CO2 into the atmosphere, nature tries and remove it again. And then just like the physical system, on top of this we've got other feedbacks around ocean circulation, solubility, vegetation changes, permafrost and so on. And again, what we know from modelling is that these provide an amplifying feedback. and some of the terms can be positive or negative, but overall these are a positive feedback. So again, climate change amplifies the amount of CO2 in the atmosphere. So there are some very strong similarities then between the physical system and the carbon cycle, and this is what drove a lot of the analysis initially. But what we find, if you kind of start looking in detail, the real fundamental difference is where the uncertainties lie. So this is the paper by Jonathan Gregory, and we can see on here, if I get my cursor up, hopefully you can see that the black body response, or the Planck response up here in the top left, is extremely well known. So there's very little uncertainty in that, and all the uncertainty in the physical system comes from these feedbacks, so the cloud and the albedo and the heat uptake, and it's the combination of those that give what Jonathan terms in this paper as the climate resistance. So that's kind of what you can think of as the climate sensitivity, and nobody in their right minds would try to reduce the uncertainty in the black body response. So all the focus goes in these feedbacks. But the difference when you look at the carbon cycle is that this negative response, the response to CO2, has quite large uncertainty. So this is where it really differs from the black body response. So in the carbon cycle feedbacks, the uncertainty comes both from the negative feedback and the positive feedbacks. And I think we made the mistake initially of focusing overly on where the positive feedbacks from climate came, and we forgot this huge uncertainty over here in the negative feedbacks. And I think we're hopefully starting to realise and redress that a little bit now, but that's worth keeping in mind. So quick recap of the history. So the C4MIP dates back to the first multi-model analysis in 2006, a large model spread, and the need to consider now the carbon response to CO2 as well as climate. And hopefully then we can start to look at some of the more latest results. So if we dig into C4MIP, we have this feedback framework, and the three kind of components of that are the fact that CO2 drives climate change. So in a linearized framework here, delta T is just proportional to the change in the atmospheric carbon. This term alpha is effectively the transient climate response. And then the carbon stores, delta C, both in the land and the ocean, are driven by changes in the CO2, so that's the term we call beta, and changes in climate, which we call gamma. And we run a handful of climate simulations where we can either vary both the climate change and the CO2, with sort of what we call a fully coupled system, or you can hold different components constant. So the biogeochemical runs are where we only vary the CO2 that's seen by the carbon cycle, and that helps us diagnose this beta term independent from the gamma. And back in AR5, we came up with maps of these things, so you don't just need to look at global totals. If you want, you can come up with these things at a grid point level, and you can see, so the top panel there is the response to CO2. It's quite large and positive everywhere, and the bottom panel is the response to climate, and that's globally negative, but there are some regions, particularly in high latitudes, where that's positive. And these models, certainly at that stage, don't include any kind of permafrost carbon release. So this is kind of, warming stimulates plant growth in these sort of high latitudes. And again, you can see from these zonal mean plots that the uncertainty comes from the land components in green. So these bars are much wider than the ocean components in blue. So that's the background. What we don't have yet is any maps for CMIP6, but what we do have is some kind of global totals. So the land and ocean uptake, so this is a paper by Vivek Arora at the moment. We've got 11 CMIP6 models in here. And if you look at the uptake, they're similar between land and ocean. So the fully coupled runs are in blue here, somewhere around 600 petagrams by the end of the 1% run. But what we do see is both the land has a stronger dependence on CO2 and climate. So the difference between the blue and the green is bigger for land, and the difference due to climate change of these red runs, they're stronger on land. And we also see that land has a greater spread than the ocean. So this is very much in keeping with what we've seen before. And we can use these runs to calculate the beta and gamma metrics. So by looking at the model spread, so on here, it's slightly kind of busy plot, so I'll try and explain this. So the dots here are the strength of the beta term, so the land carbon response to CO2. And as we move to the right, this is a stronger response to CO2, and each dot on here is a model. So you can see the multi-model mean of 0.97. But we can split that now into models with and without a terrestrial nitrogen cycle. And that's one of the big developments across models. So CESM in CMIP6 was the only model with a nitrogen cycle, so Peter Thornton will remember that well. But now we've got approximately half the models have a nitrogen cycle, so you split out the models with a nitrogen cycle tend to have a smaller response and a reduced spread. So this kind of red bar is smaller in extent than this brown bar. And the same is true for the response to climate. So the gamma term down here to the left, again, you see quite a spread across models, these individual points. But the nitrogen models both have a weaker response to climate. So this time, stronger response is to the left, it's a negative term. And the models without a nitrogen cycle tend to have a stronger response and a greater spread. So the inclusion of a nitrogen cycle has actually kind of condensed the model's behavior. Okay, if we have a look at the ocean, so the same plots now, but these are the ocean response to CO2 and climate. The ocean response to CO2 is actually very similar to CMIP6, and similarly the ocean response to climate is very similar to CMIP6 as well. What we've done in the paper is explore sensitivity of these numbers to calculating them by different methods. So you, as we talked about before, you can hold different parts of the system fixed, so you can vary just the CO2 or just the climate or both, and you can diagnose the beta and gamma terms by different pairs of runs. And as recommended by a handful of studies, primarily one by Jörg Schwinger from CMIP6, the preferred method is to use the difference between the coupled and the biogeochemical run. So these runs here have a stronger sort of diagnosed impact of climate. This is particularly important for the ocean. So climate suppresses uptake of new carbon more so than it releases existing ocean carbon, which is what you get if you use the radiatively coupled runs. Okay. And so I won't go into details on here, but just to highlight now that the analysis we're doing then digs much deeper into some of the component level behavior of the models. So Vivek's paper is in Biogeosciences discussion, so the discussion for that is closed, but you can still see the paper by this link at the bottom. It's 100 or so pages long if you really want to dig into some of the details, but we felt it was really important to bring together all of both the land and ocean in a kind of an overview paper. So we've got figures on the land, breaking the response down into the vegetation and soil components, and then different bars here for the GPP response, the allocation, the residence time, and then over here on the right we've got breaking the ocean response down into response to the saturated carbon and the disequilibrium terms, and their response to warming. So there's a huge amount of information, and we're only really beginning to sort of scratch the surface. So hopefully this will lead to a lot more analysis going forward. I'm going to say a couple of words about the historical runs. So the runs so up to now are just diagnosing the feedback, so these 1% per year increase in CO2. Analysis and evaluation is only just beginning really on the historical runs. I suspect there's a lot going on that I'm not aware of. But one thing I want to highlight really is both what I think is an inconsistent treatment of land use across models. So we still don't fully understand what models do to incorporate land use change, and that complicates analysis of the carbon budgets. And also I think we need to be aware of showing plots that only show changes in the carbon stores when these hide very big differences in the baseline state. So I'll show you what I mean by that in a minute, and that's something I think the community really needs to do a bit better on. So not dissimilar to CMIP6, if you have a look at things like plots of GPP on land or the ocean uptake, there's clearly a model spread, but models tend to do the same sort of thing. And by present day, observational estimates of GPP are somewhere in the vicinity of 120 or so petagrams of carbon, and the models tend to be within about 20% of that. So, ballpark, they sort of do okay at a global level. Similarly, in the ocean, the long-term ocean uptake is fairly consistent between the models. What we're starting to see is some models that don't start at zero for their ocean flux. So the CNRM model stands out here, and that's because they include some lateral flow terms. So the CNRM model has some river transport of carbon that takes carbon from the land into the ocean. So there's a constant additional flux into the ocean, which means at steady state, their kind of ocean atmosphere exchange is non-zero. And again, this is something that, by making the models more complex, also means we have to be aware of this in their analysis. So you have to, obviously, if you're doing analysis of multi-model carbon fluxes, you need to somehow treat the fact that they don't all include the same processes. When you look at changes in the carbon stores, again, so this is what I was talking about, inconsistent treatment of land use. So you could sort of break this vegetation carbon plot into three clusters. So there's a cluster of models here that appear to have quite a strong response to land use change. So they have a fairly strong release of carbon during this early part of the 20th century, so that they're kind of carbon negative in total by present day. Then you've got a cluster in the middle that have a slightly weaker response and are approximately carbon neutral by present day. And then you've got a couple of models up here that I suspect don't treat land use at all. That was certainly the case in CMIP6, that some models didn't have a land use change component. So again, there's a big spread in these changes. But what's also important to look at is the absolute values and not just the changes. And when you do that, you can see in the vegetation carbon, there's a really big difference in the total amount of vegetation carbon. There's a factor of 2 different between the low and high models here. And in the soil carbon on the right, it's even worse. There's a factor of 5 difference. And even though there's, sizable uncertainty in observed kind of carbon pools, I think it's high time we started kind of being a bit more honest about the fact that some of these models are simply wrong. We know there's more than 500 petagrams of carbon in the world soil. So it's hard to understand how the models can all be within about 20% of their global GPP values, but a factor of 5 different in their carbon stores. And it's partly because I think we overly tune and evaluate fluxes, and we forget about the stores and the residence times. So that's kind of one of my key points that I try to make, is that we really need to get the residence times and the turnover of the carbon pools much better considered in the models. Okay, right, so that was an overview of the results from C4MIP. Now I'm going to show some analysis digging a little bit into the sources of uncertainty in those feedback terms and how that's changed over MIP generations. So this is some analysis I've been doing with Pierre Friedlingstein. So just to remind you, this figure, we had this initial focus after the first C4 MIP generation, looking at the climate feedback gain, G it was called, and I think the comparison with physical feedbacks led us to kind of fixate on this a little bit and forget some of the other uncertainties in the system. So what you can do, and what we did right at the start, is that the gain, G, can be expressed in terms of the alpha, beta, and gamma metrics. We know that, so this equation for G was part of the initial kind of Friedlingstein et al. Feedback terms. But we can also do the same for kind of perhaps more relevant metrics like the airborne fraction, so the fraction of CO2 emissions that stay in the atmosphere, and for TCRE, and we can express those as well in terms of alpha, beta, and gamma. And the K here is just a constant, it's a unit conversion. So alpha, beta, and gamma control both the carbon cycle gain, but also airborne fraction and TCRE. And if you construct TCRE from those feedback terms, you can see this kind of line here. It's an extremely good fit, so that these equations really do hold quite well, and you can go back across 3 generations now of these multi-model ensembles, and all of the all of the models, even though they ran different scenarios. The original CMIP was not a 1% run. We can still calculate and reconstruct the TCRE values really quite reliably. So that's quite nice. So that means that allows us to propagate the uncertainty in each of the feedback components through to some of those terms like airborne fraction and TCRE that we care about. So the plot here shows the different generations of models from C4MIP through to CMIP5 and CMIP6, and how these different feedback metrics have evolved in time. So the red plots here are alpha, so this is the response to climate. One thing we see in CMIP6, there are more models at the high end, so that reflects what we know about the climate sensitivity in CMIP6. We're seeing some higher climate sensitivity models. The UK model is in there, as is E3SM, I believe. When we look at the carbon cycle response, so in green we've got the beta terms, land over here on the left and ocean on the right, and the gamma terms in blue. So again, we can see how those have changed. So there's definitely a collection of points when you look at the land beta that seems to have compressed the uncertainty. So we just got one model up here, but apart from that one model, there's a reduction in the spread of the land betas. And again, as I said earlier, some of that's coming from having a nitrogen cycle in more of the models. But when we kind of transfer these kind of changes in the terms into these aggregated terms that we care about, then we can see which of those actually dominate the uncertainty in some of these feedback factors. So if we care about the climate carbon gain, the G, we can see that this is dominated by these blue bars. So that's gamma, in particular gamma land is the darker blue and gamma ocean is the pale blue. And as we look at these three top blue bars here, these are the different generations of C4MIP at the top, CMIP5 and CMIP6. And then this slightly thicker bar is combining all of those together. So this is kind of what we already knew, that the gain was dominated by gamma. And if we want to reduce uncertainty in gain, then we need to reduce uncertainty in gamma. And I think that's kind of been a little bit of a red herring for a while. If we want to know more about the airborne fraction, so how much more of our emissions stay in the atmosphere, the airborne fraction uncertainty is dominated by beta. So it's actually the drivers of the sink to start with that are the big uncertainty. And then when we get to TCRE, which arguably is what we really want to know if you're talking about carbon budgets, the uncertainty there has kind of traditionally been split 50-50 between the climate response, so that's the red bar here, the alpha terms, and the combined beta and gamma, so the carbon cycle terms. So there's some literature on that by Ben Booth and Chris Huntingford and others that kind of came up with this kind of quite nice conclusion that carbon budgets are approximately half and half determined by physical uncertainty and carbon cycle uncertainty. But what we see as we move to CMIP6 is that's actually changed quite markedly. And the CMIP6 bar here now is kind of much more dominated by the climate uncertainty. So this is a combination of greater spread in model climate sensitivity and reduced spread in the carbon response to CO2. And that's kind of quite a shift in these results. Although, interestingly, what we find when we look at the spread is that the spread in TCRE is not actually that different from before. So what we've got is sort of two competing sort of changes since CMIP5, that the airborne fraction has, in terms of the standard deviation across models, less than half the spread that it had in CMIP5. So we've actually reduced the uncertainty in the carbon cycle part of the component by about half. But the increase in climate sensitivity and uncertainty in that from models means that TCRE overall has a very similar both mean value and model spread to CMIP5. So these kind of competing changes mean that in terms of what we say about carbon budgets, CMIP6 on the face of it doesn't look very different to CMIP5, although the reasons behind some of the results are different from what we had before. Okay, so I'm conscious of time, so I'm going to move on and talk a little bit about CMIP. So this is something that sprang up much more recently. So it's what I refer to as a MIP in a year. And it sprang out of a workshop last January in Vancouver that followed an IPCC meeting. A sort of small group of people were discussing carbon budgets. And it emerged that the zero emission commitment was a vital part of deriving carbon budgets, but wasn't really catered for in any of the CMIP6 experiments. So pretty much on the spot, we decided to see if we could kind of muster a few models to do some simulations. We didn't really expect too much in the way of take-up, given how busy modelling groups were. But by May, we had a protocol paper submitted, and by October, it was published, and we had some space dedicated on the Earth system grid. And then by December, we had an analysis of models starting to come in. Remarkably, we had 18 models. So we had 9 GCMs and 9 EMICs, and all credit to Andrew McDougall for pulling this together and getting it submitted in time. But to go from kind of idea through to delivery in less than 12 months is really quite remarkable for a MIP of this size. So the idea behind CMIP is to address the question of how does climate continue to respond following a complete stop of carbon emissions, and kind of partly to address this myth that there is some warming locked in or warming in the pipeline. It's sometimes referred to that if you stop emitting, the world will carry on warming for a while. So there's a fair amount of literature going back to work by Ken Caldera, Damon Matthews, and others, but actually suggests that if you stop emitting, the trade-off between continued ocean heat uptake and removal of CO2 from the atmosphere means that the climate response will be approximately stable, so you might not get any subsequent temperature change. So we came up with some experiments. So there's both what we called our A set of experiments, where you follow the 1% increase in CO2 up until you've emitted 1,000 petagrams of carbon, and then you suddenly stop, and you model the subsequent decline in CO2 concentration and the temperature response. And then we have a B set, where the emissions gradually increase and reduce again, but emit the same amount as the A set. So we're looking to explore both the state and the rate dependence. And what we find, particularly from the sudden cessation, all 18 models, not surprisingly, see a rapid initial reduction of CO2. So the natural carbon sinks persist and the CO2 in the atmosphere decreases. So from the moment you reduce, the moment you stop emitting, your CO2 starts to reduce. And then the subsequent warming to that, that's the panel over here on the right, you see models kind of cluster around zero, and some models cool, some quite markedly, 0.5 degree or more. Some models continue to warm, but there's this committed change relative to the stop point tends to cluster around zero, and you can measure it on different time horizons. So up here, 25 years or 50 or 90 years. Typically, it's kind of very close to zero, plus or minus 0.1 or 0.2. So this is kind of very consistent with the IPCC's assessment of assessing the zero emission commitment as zero. But now we've at least got some kind of process-based backing to understand why that is. And Andrew's paper digs into a little bit, tries to explore. So the models here are shown from left to right in order of their zero emission commitment. So the black bars down here show the strong negative ones on the left and the positive ones on the right. And we can break down the terms into their continued ocean uptake of heat versus their carbon sink. And there's no systematic pattern of whether the heat and carbon uptake is weak or strong. And similarly, there's no systematic pattern in whether it's dominated by land or ocean sink. So we've kind of got some understanding of the terms in the process now, but not yet a full recognition of what makes some models have a positive or a negative zero emission commitment. But we can at least be a bit more confident when we say we make assumptions that it's pretty close to zero. Also, it appears to be state dependent. I'm not going to dwell on this, but for full details, you can see Andrew's paper, and again, that's in Biogeoscience Discussions. So quick synthesis, what does all of this mean then for carbon budgets? So we said that the carbon cycle was key to 3 of the 5 components of the 1.5 carbon budget framework. So zero emission commitment actually is close to zero, so that's no change to the assumption, but now we feel a lot more justified in actually being able to say that. TCRE, as I sort of explained, there's no change in TCRE magnitude or spread since CMIP6, which might sound a little bit boring, but underneath the hood, there is quite a big change in the source of the uncertainty. And in particular, I think the nitrogen cycle components of the land models has reduced the spread in the carbon response to CO2. But that leaves a greater role for the climate sensitivity. And then the final one is quite interesting. So this idea of missing processes. So permafrost is still not accounted for in most ESMs. But now we've got a situation where the nitrogen cycle is partially accounted for. And that's not a situation that the carbon budget framework allows for. So it allows you to diagnose TCRE from multi-models, and it allows you then to adjust for a missing process. But it doesn't tell you what to do when half of your models have a process and half don't. So it's a bit of a work in progress, how to actually account for that. So at the moment, we're just taking the whole CMIP6 ensemble at face value and using that to define TCRE, but there might be some way of propagating some nitrogen cycle behavior from the nitrogen models to the non-nitrogen models. Okay, so overall, what's been a success and what's not? So CMIP6 has been hugely challenging. It's been a big step up from CMIP5, more complex models, more MIPs. Every time you move, somebody comes up with another MIP, including the carbon cycle guys. There's been a much bigger data request. It's been hugely complex, and it certainly feels in the UK like the timelines to deliver it are shorter. So I think getting anything at all out within CMIP6 and the IPCC publication deadlines has been a really major success. So big debt of gratitude to everybody who's been working on this. The land carbon models are still, I think, almost embarrassing in terms of their spread and their disregard for calibrating carbon stocks. And I think that's a really high priority the community would like. I would like to see them do more. Have we reduced uncertainty? I've sort of given that a sort of qualified tick, maybe not quantitatively, but I think we better understand some of the processes. And I think for the carbon cycle we have, and by actually adding more complexity to the models, it's fairly rare that that reduces uncertainty, but it certainly appears to have reduced the spread between models. And whether or not you properly count reduced spread as reduced uncertainty, they're not exactly the same thing. And I think we're going to need a round of kind of process evaluation. But before I finish and go on to my conclusion slide, I'd just like to kind of give a reminder of what we mean when we talk about complexity. So it's very tempting, having put years of effort into running these models, and they take weeks and weeks to run on a massive supercomputer, that we then boil everything down to a global number. And it's easy to forget the huge amount of detail that goes on inside them. So I thought it's actually quite instructive to look at some of the really kind of detailed behavior that's going on. So this is the surface CO2 concentration coming out of the UK model hourly. And this was inspired, some of you may have seen, there's a really nice NASA animation of observed CO2. So this is kind of like a model equivalent of that. And as you step through, you can see a diurnal cycle sweeping around the world. You can see, particularly kind of sweeping across the Atlantic here, there are kind of plumes of CO2 coming off North America that get into weather systems and get into kind of that North Atlantic storm tracks and swirl around a bit. So we mustn't forget that the models actually are made up of really, really fine scale detail. And then this obviously ticks along. I'm going to switch now from hourly data to daily data, and we can flick through here, and you can see the seasonal cycle kick in as well. So as we go through, this is March into April, coming through to May, you start to see the Northern Hemisphere growing season kick in. So these darker colours becoming apparent now. And I worked out something like for every time I plot an annual mean global CO2 concentration, it's got something like 60 billion data points have gone into it. So it's really kind of instructive to look at this kind of behavior and remind ourselves of how complex the models are and just how much they actually do look like the real world. So I think that it's really quite instructive, almost hypnotic sometimes, to watch these animations. Right, so on to the conclusions then, and then I'll take questions. So CMIP6 is the third generation now of our coupled climate carbon cycle modelling. The headline numbers are not hugely different from CMIP5, but I think some of the model behaviour is different, so that kind of hides the fact there has been progress. So this confirmation of zero emission commitment to zero and understanding the mechanisms of it is really good. The increased complexity in the land models, I think, has led to a reduced spread, and therefore TCRE, I think now we understand more what controls it. I think some of the processes now are back to the climate modelers in terms of some of the cloud feedbacks. And for next steps, definitely I think we need to improve representation of the carbon stocks on the land models. I haven't talked at all about emergent constraints, but certainly that's an area of kind of active research. We can use variability in the real world to constrain some of the model responses, and coming up with ways to treat mixed complexity in our multi-model ensembles, hopefully towards kind of improved carbon budgets. So that's what I'd like to see. So I'm going to wrap up there, stop talking for a while, and thank you for your attention. I'm happy to take questions.
Thank you, Chris. I'm going to stop the recording.